Somewhat related to the idea of speculation is software transactional memory. And it's sort of time travel-ish in that, what actually happens is that a group of changes are carried out on a speculative basis. That is, we assume they'll all succeed. We'll check afterwards if everything went okay and retry if necessary. So this is intended as somewhat of an idea that is proposed as an alternative to locks. And so instead of that, we have transactions that take place on that memory. And the analogy, something to compare this against, is database transactions, which hopefully you learned something about if you took a previous databases course, which I think is most people, but not necessarily everybody. But the idea with the transaction is, we package up a group of changes all at once, and we will expect that either this whole package is completed or it's rolled back. It's as if it never happened, and we potentially try again. And software transactional memory says instead of just applying that to database tables and rows and things like that, we could do the same with memory in our software. And this is not a particularly new idea, but it has recently seen some renewed interest. And the basic idea is no different than what we saw in database transactions. We're going to package things up as a series of memory operations all within one transaction, and either they all succeed or they fail and are later retried. It is potentially a simple programming model, and we'll see we have a couple of examples of how to do it. There's a library for this in Rust, although I can't necessarily vouch for its quality or usefulness. But the first thing that you do is just create a transaction. You write it as an atomic block. And therefore, you don't have to think about lock granularity, you don't have to think about deadlocks, you don't have to sweat any of those details. You just get this transaction written, and then it's the responsibility of the implementation to ensure that the code operates as an atomic transaction. So it's always nice if you can give away the problem a little bit. So here's a simple transaction with an atomic block, and that we will say let x atomically, and then we specify the name of our transaction here as trans, and we write in the context of this transaction 42 into this variable, and then we read it back and we get the result at the end. Okay. This isn't a super illustrative example. We'll do a better one shortly, but the idea is that you say atomically, and this Rust STM library is how we do this. And we say atomically, and we have a little closure that says here's what we want to be the atomic block. So stick everything in it and hope the compiler and the implementation does what we expect it to do. All right. Here's a better example that gives you what we are looking for here. We have an account. An account has a balance, as before, and in this case, it is a transactional variable, so tvar, which says that it is supposed to be accessed using software transactional memory, and we have the wrapper here where it takes the balance is going to be a 32-bit floating point number. We'll assume, I guess, Bill Gates doesn't bank here, and a 32-bit float is enough to contain his account balance. In any case, so the transfer funds function takes two accounts and the amount. All right, that is in line with our standard example here, where I'm sending my friend $50 to repay them for something. All right. Easy. So we will then have an atomically block, and we will say that our transaction here is called TX, and we're going to then read the sender balance, so sender.balance.read with our transaction, receiver balance is receiver.balance.read, and then we will update the sender balance, the sender balance being the new value subtracting the amount, and the receiver with the new balance including the amount. And then we return OK, and everything is done. It is important to note, actually, bank account transactions aren't actually, strictly speaking, atomic. Taking the money out of your account does not happen in the very same instant as it is deposited in the receiver's account, as you will probably know if you have ever tried to send anybody money. But pretend for the sake of the analogy. And with software transactional memory, you'll notice we don't have to think about acquiring the locks here, so there's no concern about, okay, well, do we have the account mutex, and did we make sure that we acquired them in some consistent order to prevent the possibility of deadlock if this kind of thing happens at the same time as another call that is doing the same thing but in the opposite direction. That won't happen. So that actually relieves some of our worries when it comes to writing this, and it saves us also from having to think about, do we have a big global lock that serializes our program, or do we have a different lock for every account where we risk deadlocks or have a lot of overhead. All that is avoided. The thing is that rollback is the key strategy here if something goes wrong. If we are trying to modify the balance of an account and we can see that somebody else has modified it in the meantime, we roll back our transaction and we start it again from the beginning. Rollback is good, but not everything can be done in this atomic fashion because, for example, writing to the screen or sending data over the network can't realistically be undone. It can't unhappen. And so not everything in an atomic block is necessarily going to be perfectly rolled back, so there are limitations on what we can do in there. There are occasional headaches about nested transactions. If you talked about it in databases, you probably did cover the idea of nested transactions. The idea is having one transaction that takes place inside of another. And what do you do if you commit an inner transaction but abort the outer one? The clean facade that you're provided by transactions kind of breaks down in the presence of nested transactions, so the Rust library actually will throw a panic at runtime if you try to nest transactions. So that's one way of dealing with it. Handle this problem by saying it's not supported, we don't do that, sorry. The other thing to note about transaction size is that some implementations, especially any of them that rely on hardware to do it, have size limits for how many things that you could do in your transaction. However, the actual problems that we face are potentially even worse than this, as we'll see in a little bit, because, well, let me explain a bit about the implementation to make it clear. So in an atomic block, we record all the reads and writes to a log, and at the end of the block, the running thread verifies that no other threads have modified any values that have been read. Basically, we are going to look at what we're doing and check our work at the end. A transaction, if you've heard me describe it in the context of a database or you've read my database notes, is basically we write down a list of here's the things we're going to do, then we do them, then we review our work to make sure that everything is okay. And if validation is successful, changes are committed, so they become permanent. Otherwise, the block is aborted, we undo anything that needs undoing, and we try again. So if the balance was updated, we will abort, we will try again so that we read the latest value for the balance, and then do our calculation correctly with the new value, which makes it work. The only problem is that software transactional memory doesn't protect against data races because its only strategy for dealing with any problem is a rollback. Unlike a database where this is happening inside the database server, in STM we can get intermediate states being visible. And that is highlighted here in this example where we have on the left function what could go wrong and on the function right, oh no. Where in the left function we will try to atomically increment the values of x and y, right? Given these two variables, we will read the old value, we will write the new value as old x plus 1, old y plus 1, and we say okay. So on the right side, we are in this transaction reading if x is the same as y, then everything is fine. Otherwise, we enter into, say, an infinite loop, and I've just written cursed thread here to show how things are. So this example, if initially x and y are the same value, will be okay. However, if we have multiple invocations of what could go wrong, Part of the problem is that the intermediate state of x or the intermediate state of y could become visible by reading those values in the other function oh no. And even though one of the implementations that tried to modify x and y at this time will fail, we will end up with the infinite loop in the oh no function, or even if just what could go wrong partially runs and that intermediate state is visible, even if there's only one invocation, because rollback is the only thing that works here. The database prevents this by not allowing you to read those intermediate values if x and y are in the transaction. Then you can't read their new values in some partial state where x has been incremented but y has not. But software transactional memory gives you no such guarantee, and you may end up with this kind of example. That may or may not happen in the Rust implementation, but it definitely does in C and C++ versions of software transactional memory. The other thing about STM is that, well, it's slow. A lot of research is going into it of late, but there may or may not be significant benefit to doing so, and it may never really work out to be that much better than other techniques that we know of, but it is an interesting idea, and it is kind of a form of speculation, and so we think it is worth mentioning. And the important takeaway is that we are operating by completing an atomic block or retrying. That is, we speculate that we will be able to make all these changes, and then afterwards we check and see if that was correct. If it's not, then we go on and retry. If we were correct and everything worked out, then we're done, and maybe we saved some time because there was no need for locking or other such synchronization. Not too bad.